field. With respect to two operations, with respect to
two operations.
plus and dot, yes. Plus is called vector addition. Sorry, addition we call not vector addition. Sorry, it's a simple addition, and dot is called multiplication. When you say it's f comma plus, if f comma plus is an abelian group.
With respect to addition.
Yes, with respect to addition. And f comma dot.
Dot also abelian.
0.
Abelian with respect to multiplication.
F minus 0. F minus 0. F minus 0. Here, what is 0? 0 means additive identity. F minus 0 should be an abelian group. An abelian group. Here, 0 is additive identity. Additive means here addition we have no additive identity with respect to identity with respect to that addition. Is that enough, or are we missing something? So there is something we should also have compatibility distribution laws between these two. So A, B, C belongs to, and A, B, C belongs to F. A dot B plus C equal to AB plus AC, and it's anyway commutative. So any another property, yeah, yeah, that's all. So since it is a commutative, so this is also implies B dot C, which is also implies B dot C into A. B plus C into A dot A equal to B dot A plus C dot A, because it's commutative group now. So we have this property. So first one is enough. This one is enough. Automatically second one follows. So if you have a set, non-empty set satisfying these three property, 1, 2, and 3. So we call it as a field. So examples, can you give me one example? Anybody know? So examples are real numbers, set of all real numbers with respect to usual addition, usual multiplication. It's a field, right? And Q, set of all rational numbers, Q comma plus dot. It is also field. So why R comma plus comma dot is a field? Because R with we already seen R comma plus is a abelian group, that we already know. And if you take dot multiplication, so every non-zero element in R has an inverse, and one is the identity, R minus 0. R minus 0 we write R star. And we abelian group, sorry. And then we already know that B plus C dot A is equal to BA plus CA. This this property also we know this in the real numbers. That's why it is a group. Similarly, Q comma plus comma dot is also it's a field. Q comma plus comma dot is also field. And C comma plus comma dot. C is a set of all complex numbers. It is also field. And we also have F comma. Another one is, do you know any other field other than this three? ZP, there is something called ZP. Z subscript P with respect to addition, modulo addition, P plus P and dot P. This is also a field if P is a prime. P is a prime number. Do you know about ZP? ZP you will see in the group. Okay, I think we don't need much about ZP, but in CSR somewhere they may ask about the field ZP, but in JL, I don't know whether they ask in this one. So we will see if it is required. I will define when I will do the problems related to ZP. I will explain about ZP. So these are the standard fields we need. One is first one, R comma plus dot is the field of real numbers. Q comma plus comma dot is field of rational numbers. C comma plus comma dot is called field of complex numbers. These three fields we need. Once we have a field, then we are ready to define a vector space. So vector space so now we will fix a field. Let F be a field. We will fix a field throughout the course. Be a field. So field means it's all the properties which are above satisfied. And you have to remember, zero is a zero F or zero is a zero element in F. Identity zero element means additive identity in F, and one means one is multiplicative identity. We know that field means there are two operations. One is addition and multiplication, right? Zero is the identity with respect to addition. One is the identity with respect to multiplication. This we will be using these notations. So now we'll start. We'll give the definition of vector space. Yeah. Okay. A vector space V. A vector space V over the field we say that we have a one set non-empty set V and over the field capital F. So we are going to define a vector space over F. What is this? It consists of vector space over the field F consists of the following. What do you mean by that? So vector space over a field means there are two things. One is non-empty set V. One, a non-empty set V. What do you call a non-empty set V of objects? The objects in this we called as vectors. Yeah, and there are two. There will be two operations. Second one operation on V called vector addition. One operation on V called as vector addition. Another operation, operation plus. This operation we denote with plus. Plus is an operation from V cross V to V, and another operation dot called as scalar multiplication. This operation is not an operation on V. It is an operation from F cross V. It is a map from F cross V to V. So that means you take one scalar, scalar means elements of field we are calling scalar, one scalar and one vector. Elements of V, if you operate, you will get another vector. Satisfying this plus and dot should satisfy the following. U plus V belongs to V. For all U comma V belongs to V. So it's like maybe I will write the first thing, satisfying such that V comma plus is an abelian group. I should have written like this first. Say abelian group, that means you know what you mean by that. If u comma v is there, u plus v should be there. And it should be associative. U of v plus w is equal to u plus v plus w. And there exists a unique vector 0v, unique vector 0v in v, such that 0v plus v equal to v plus 0v equal to v for all v belongs to v. So here 0v we call a zero vector. Okay, 0 means it is a zero element in field scalar, but 0v is a zero vector. And another property is that for every v in v there should exist additive inverse. That means negative v. For every v in v there exists unique vector minus v in v such that v plus of minus v is equal to minus v plus of v equal to 0 vector 0v. And I said it is a commutative, that means u plus v is equal to v plus u. So addition, with respect to addition, we should be abelian group. And there is scalar multiplication also. Scalar multiplication should satisfy this following property. If alpha dot v should be, for every alpha dot v belongs to v, for every alpha belongs to f, v belongs to v. And alpha times u plus v is equal to alpha u alpha v. And alpha plus beta, this kind of distribution law. So scalar multiplication over vector addition is distributed, that kind of thing, right? Alpha plus alpha times u plus v is equal to alpha u alpha v. Another way also we should have alpha plus beta times u, that means scalar multiplication dot is equal to alpha dot u plus beta dot u. Another one is alpha times another one is alpha times alpha dot beta dot u equal to alpha beta dot so here see alpha dot beta dot u, here this dot is a scalar multiplication, and here alpha beta we have now alpha beta from where? Alpha beta from f. Here I forgot to write here. Alpha beta belongs to f. So what do you mean by alpha beta? This is a multiplication in the field, and u is a vector. U belongs to v. So alpha beta, it's a multiplication in the field, and this dot product is a scalar multiplication. So this condition should be satisfied. Okay. So, and another last property, 10th property. 1 into v, 1 dot v. One means, you know, one means it's a unity in the field, identity element in the field. 1 into v is equal to v into 1 is equal to, sorry, v dot 1 won't be there. Scalar multiplication is v is a vector. 1 into v equal to v. For all v belongs to v, and 1 is anyway, 1 is identity element. Okay, now we will see example. Here I forgot to tell you what you call elements of V, vectors. And elements of field F we call scalars. You have to remember this terminology. Elements of V are called vectors, elements of F are called scalars. So now very basic and fundamental example is Fn. Example, we will say example. Fn. F superscript n, F superscript n with this is n. So what is this? This is defined by F is any field. So Fn is defined by, it's n tuples of fields, field elements, n tuples of n tuple space, maybe we call n tuple space. This is defined by Fn equal to like Rn. If f is equal to R, Fn is Rn. How do you define Fn is equal to x1, x2, so on xn? Where x1, x2, so on xn belongs to f. X belongs to, now we are going to define addition and scalar multiplication. X belongs to Fn, Y belongs to Fn, X belongs to Fn, Y belongs to Fn. So X will be of the form x equal to x1, so on xn. Y1, Y is of the form y is equal to y1, y2, so on yn. Then we are proposing vector addition. The vector addition is x plus y. Vector addition. We will write first vector addition. Vector addition is proposed by x1, x plus y is equal to x1 plus y1, x2 plus y2, so on xn plus yn. Then you should ask, what is this place? X plus x1 plus y1. X1 here, I forgot to tell you, x's and y's are f, right? So what do you mean by x1 plus y1? So this is a addition. This is a addition in the field. X1, y1 belongs to field, right? So these are the addition in field. Okay, this is understood. So it is these are addition in the field f, addition in f. Now scalar multiplication, alpha scalar multiplication. What is the scalar multiplication? Alpha f. Equal to alpha x1, alpha x2, so on alpha xn. ఇక్కడ మీరు అర్థం చేసుకోవాలి, ఆల్ఫా x1, ఆల్ఫా x2, ఆల్ఫా xn ఉందంటే ఆల్ఫా, హియర్ ఆల్ఫా is f, alpha is in f, xj's are also in f, right? So then in f we have a multiplication f. So this alpha x1, alpha x2 are the scalar multiplication in f1 only. So this is understood. So we can verify that Fn is a vector field. We can verify that. Verify that Fn is a vector field. So vector space over f. What is the zero vector here? Can someone tell me what is the zero vector?
0, 0, 0, dot
0,
0, 0, so on n numbers.
And minus x is minus x, minus x.
Minus x1, minus x2.
2
So on minus x. Yeah. So it's a very fundamental example. If you, so if f is R, then it is Rn. If f is C, it is Cn. So if you have a field, sorry, now I want to give some terminology, basic terminology. If E is a vector space over R, over field of real numbers over R, then we call it's a real vector space. Then V is called real vector space. If V is a vector space over C, we call complex vector space. So, and another example is space of all matrices, f of m by n of f. F of m by f, m of f, m by n of f. Sorry, m space of all matrices over m, that is denoted over f. Yeah, this f of m by n of f. This is a space of all matrices m by n matrices over f, which is defined by equal to set of all matrices m by n matrices, matrix over f. over F. That means it is a set of all m by n matrices whose entries are coming from field F. So this is also vector space with usual addition and usual multiplication. Is a vector space. What is the usual addition here? Suppose if you take A is equal to Aij, B equal to Baj, what is A plus B? Somebody said. What is the usual addition here? Usual addition and scalar multiplication. A is a matrix. Let A is equal to Aij. Capital A equal to Aij. Capital B equal to Baj. Both are in this set. Then A plus B. How do you define A plus B? You have to add component wise. Corresponding elements you have to add. A plus B is Aij plus Baj. And what is the scalar? This is called usual addition. What is the scalar multiplication? Alpha A equal to alpha Aij. Alpha into Aij. Alpha. I should write alpha inside the bracket. Yeah. So with respect to this addition and scalar multiplication, it is a vector space over F only. So this is a vector space over F. So if you take F is equal to R, it's a real matrices, and if F is equal to C, this space is called complex matrices, space of all complex matrices. Now there is another fundamental example, F of X. It is a set of all polynomials with coefficients from F. With coefficients from F. F of X, how do you denote? And the set theoretically, F of X is equal to F bracket X equal to summation AK X 4K. K is running from 0 to N, where AK are fields from the field, and N is any zero natural number or 0, 0, 1, 2, 3, so on. We know this. This you will see in ring theory also. This is called polynomial ring, but we are not taking as a ring. We are going to take it as a vector space. So what now I'm going to define a vector addition. What is a vector addition here? Vector addition, P vector addition for P equal to summation AK X 4K. K is running from 0 to N. And Q is equal to summation BK X 4K. K is running from 0 to N. So if suppose in the first polynomial, if An is not equal to 0, then this is called polynomial of degree. If An is not equal to 0, what do you call this P? It's a polynomial of degree N. Okay. So now we have two polynomials. I'm going to define vector addition of these two polynomials. P plus Q equal to standard way, usual way. How do you add two polynomials? We will add the corresponding coefficients, right? Corresponding powers of X 4K coefficients. So AK plus BK into X 4K. And scalar multiplication, alpha P. Alpha belongs to F. Alpha belongs to F. For alpha belongs to F. Alpha is from field. Alpha P is equal to summation alpha AK X 4K. So we just multiply alpha inside the polynomial. So this is scalar multiplication. I should have written scalar multiplication here. With respect to this vector addition and scalar multiplication, we can verify that it is a vector space. F of X is a vector space with respect to above operation. Is a vector space over F only. With respect to above operations. With respect to above operations. So now in one problem we will see. So we have seen enough examples. Suppose problem 1. I will different the vector space I am going to define. Let V equal to R plus. R plus means interval 0, infinity equal to 0, infinity. And V is a set of all positive number. F is real numbers, field of real numbers. So now we are vector addition. I am defining vector addition. X plus Y. X plus, this is a vector addition symbol I'm using, plus O plus. So this is equal to XY. For all X comma Y belongs to V. V means R plus, V equal to R plus. And scalar multiplication. Alpha dot X equal to X power alpha. Alpha belongs to R, X belongs to V. So now can you check, is it a vector space? Is V vector space over R? Is V vector space over R? Question is V vector space over R with respect to the proposed operations, vector addition and scalar multiplication? Okay, first we will see this addition, vector addition. So we need to check V comma O plus. Is it a abelian group or not? It should be abelian group, right? Is it a abelian group?
Yes, sir.
Yes. Why? Why it is closed, first of all? Why is it closed under this?
Depend on real number.
Vector addition condition lone undi కదా.
Yes, vector addition condition ఏముంది అంటే x into y. If x is a positive real number, y is a positive real number. If you multiply two positive real number, you will get positive real number or not. So మనం రెండు positive real numbers multiply చేస్తే we will get positive real number. So it is closed. And we know that with respect to addition, with respect to multiplication on real numbers is associate. So we can see that. So x plus of y equal, I will write all the properties. So product of two positive real number is again a positive real number. So therefore x plus x, this plus the special plus O plus, we call O plus x, O plus x dot y belongs to V for all x comma y belongs to R. Yes, and it is associative. It is also associative. X plus O plus x O plus y O plus y z equal to xy. This also you can verify because both sides you will get xyz. So it is true. R plus. I'm sorry, V, it belongs to V. R plus. We have to write in V, right? V. Okay, this is V. R plus equal to V. V equal to V, if you write, that is also fine. Okay, then it's a associative law, and what is the additive identity, vector addition identity with respect to vector addition? Can you guess? Otherwise, if you don't guess, we no need to guess. We'll write xy is the x O plus y is equal to x. Then we have to find out y. Y, right? We will write y here. So for all x belongs to V. So what should be y? Okay, so that means xy is equal to x, which implies
Y equal to
y equal to 1. So now you can also verify 1 plus 1 plus y, 1 plus x is also 1 O plus 1 O plus x is also x, 1 and 1 O plus. Other way also we can verify. So that means it's additive inverse is there. And what about the inverse of x? Additive inverse of x. So we have to see x O plus y equal to